This is the presentation for course CIVE 1188 Structure Analysis video project by Alex Wang. The main goal of this project is to apply engineering analysis techniques to a real-world structure under a hypothetical condition. To begin with, this pergola in my backyard has attracted my attention. In order to conduct further studies, I have measured out all the main dimensions, including the cross-sections, and finally selected one of the simply supported secondary beam to be the subject. From the measurements and the assessment details, I've simplified the real-world structure to a free body diagram, and I have mathematically described the load on the beam with a step function. And a quick note here that in order to make the units consistent, I've converted all the units into kilonewton, millimeter, and gigapascal, or kilonewton per square millimeter. Now we can derive the shear force and bending moment function by integrating the original load function. It is worth noticing that here I actually integrated negative fx, because both shear force and bending moment is actually a counteraction to the loading beam that is at equilibrium. After two integrations, we'll have two integration constants, which we'll use our first pair of boundary condition. That's because simple supports do not provide reaction moments. The moment function will be 0 at both ends. And after solving the two constants, we can arrive at this bending moment and shear force diagram. Next, we continue with another two integrations based off the relation that the second derivative of deflection is equal to the negative bending moment over EI, or flexure rigidity, which is the product of the Young's modulus of the material, multiplied by the moment of inertia of its cross-section. In order to solve for the deflection function, we still need to do two integrals, which will again result in two integration constants, and now we will use another pair of boundary condition that the deflection at both ends, which is where the supports are, is 0. By solving these constants, we can get the deflection and gradient function of the beam, hence get our max deflection and gradient, also where they actually occur. For the second half of this project, we will look at how bending and shear stress distributes and acts inside the beam. Our max bending stress will occur at the cross-section where max bending moment occurs, and the maximum tensile stress which will occur at the maximum distance from the neutral axis, or in other words, the edge of the cross-section. We then apply the formula to find this sigma max for tensile and compression stress. It's the same story for maximum shear stress, except that this time the max shear force occurs along the neutral axis, or in other words, the center of the cross-section. In order to avoid some extremely small numbers, and since we'll be dealing with stress only from now on, I've made one more conversion of the units from gigapascal to megapascal. Now, in order to find the failure plane, or at least the possible failure plane of this beam under loading, we analyze the principal and maximum in-plane stress at three critical points, where case 1 was the point where only tensile stress occurs, case 2 was the point where only shear stress occurs, and case 3 being a random point with a combined action of shear and tensile stress. By applying the formula, we can easily find the principal stress and maximum in-plane stress for each of the 3 points and their corresponding plane angle. We can now notice that the case 1 always have the maximum stress among all 3 cases, which can make us believe that the failure must happen to point 1 first. We then compare the ratio of our calculated stress to the maximum strength of wood, which is 4 megapascal and 1.6 megapascal respectively for tensile stress and shear stress. And we can notice that our tau value has a greater ratio of around 43, while our sigma value ratio is only about 34. So now we can confidently say that because of the greater ratio, under this loading condition, our beam will fail at point 1 due to shear stress exceeding the material's shear strength, and hence the failure plane will follow the plane angle for our maximum shear stress, which is 45 degrees, as marking on the beam has shown. This is the end. Thank you for watching.